Okay, in this tutorial we're going to be looking at literal and simultaneous equations. Okay, so literal equations are equations with several pronumerals, okay, and rather than having a solution of a numerical or number answer, the solution will be expressed in terms of pronumerals, which are also called parameters. Okay, so this is best demonstrated through a worked example or two. Okay, so we're going to look at solving the equation mx plus ny equals kx take z. We're going to try to solve that for x. Okay, so that's what we're going to be working through. Okay, so really, you can think of this just like an equation that has numbers. Okay, we want to get our x's on the same side. Okay, and we want to get everything else on the other side. So we're going to bring our kx across and get rid of our ny. So we've got mx take kx. Okay, equals negative z take ny. We can now take x out as a common factor. So that we've got x outside of m minus k, which equals our negative z take ny. Okay, and now we can divide by our m take k. This leaves us with x equals negative z take ny all over m take k. Okay, so you can see that we've actually found our solution. Okay, and that we've got our x by itself. Okay, and our answer is in terms of our other variables. Okay, so we'll move on. Okay, so we can look at also doing these type of things with simultaneous equations. Okay, so our next one, okay, is we have two equations. Mx take y equals k and x plus ny equals 2d. Okay, and we need to solve this for x and y. Okay, now remember we've got multiple ways of solving simultaneous equations. We can do substitution or elimination. Okay, it doesn't really matter which way you go as long as you're doing the maths correctly. Okay, the textbook, this is worked example 15, okay, the textbook uses elimination, so we might go for substitution instead and see how we turn out. Okay, so what we're going to do is we'll call this equation 1 and this equation 2. Okay, what we're going to do is we're going to rearrange equation 1 so we're in terms of y. Okay, so we're going to have y equals something. Now the easiest way will be to move our y over here and our k over there. So when we do that, we'll get mx minus k equaling y by subtracting our k and adding our y on. So I might actually call that equation 3. Okay, so what we're going to do is we're going to sub 3 into 2. So what we're going to do now is wherever we've got a y in this equation, we're going to put in this. Okay, so we're going to get x plus n times mx take k. Okay, sorry, equaling 2d. Okay, so that's what we're doing there. Okay, so what we're going to do is we're going to actually expand out these brackets here. So we get x plus nmx minus nk equaling 2d. Okay, then we're going to move our our nk away. So I might just come up here for this step. So we'll go x plus nmx equals 2d plus nk. Right, here what we want to do is we want to take out x as a common factor. So that we've got x outside of 1 plus nm equals 2d plus nk. Right, so then we can go, well, x equals 2d plus nk divided by 1 plus nm. Okay, so now we've solved our equation for x. We need to also solve it for y. Now the easiest equation to use now is this equation here, because we've already got it in terms of y. So all we've got to do is put this x value into here. So if we sub x into 3, Okay, then we're going to get, I'm just going to write this with the y to start with. We get y equals m times our 2d plus nk on 1 plus nm, okay, minus k. That is what we're going to get as our answer. Now it's in a slightly different format to what we had in the textbook, but it doesn't matter, it's the same solution. Okay, there's nothing incorrect about this. Okay, so there's no dramas there at all, leaving it in that form. Okay, so it's a little bit different to what was in the textbook, but that doesn't matter at all. Okay, so we'll keep moving on. Okay, so when we talk about solving systems of equations, so if we are solving simultaneous equations with two variables, so that what we're talking about there is we've got two linear graphs. Okay, and we've got three possibilities of how these can work. Okay, so we can get one solution, which is where we have one equation like that, okay, and some other equation, say like this, okay, and you'll see we only have one solution where they intersect. Okay, so this is one solution. Okay, and what you can notice about that is that we actually have different gradients. Okay, if we've got different gradients, we usually always have different y-intercepts. We don't have to, okay, but we usually do. If we don't have different y-intercepts, okay, then what that means is that the y-intercept is the point of intersection. So generally speaking, okay, our gradient is different. Okay, I'm just using m for a gradient. Okay, and y-intercept is different. Okay, this is for our two equations. Okay, so there is a special case where they can be the same for our y-intercept, but not very often. And the reason why I'm talking about the gradient and the y-intercept is, of course, because we can put these equations in the form y equals mx plus c. Okay, so I'll just flip over so I've got some room. Okay, we also have the other case. Okay, another case here where we have no solutions. Okay, what happens when we have no solutions? Okay, okay, our gradient, our m's are the same. Our gradients are the same. Okay, so because our gradients are the same, we're never going to come together. So think of it like train tracks. And our y-intercept, oops, are different. Okay, we have one more case. So this one is when we have no solution. Okay, and we have another case here where our two equations are actually identical. Okay, and this is infinitely many solutions. So our m and c's are the same. Okay, and basically we can use that information, okay, to actually solve different problems. So what they like to do is give you a situation and tell you that there's one solution, or what's this value going to be if there's going to be one solution, those type of questions. Okay, so we'll look at doing a worked example along those lines. So we want the value of k for our system of equations, which is kx plus 3y equals 1, and we've got 4x plus 3ky equaling 0. Okay, so we want to find k so that we have a unique solution. Okay, well, a unique solution. Okay, so that means, we're going to be back here, a unique solution, so we're going to expect that gradient and our y-intercept are different. Our gradient definitely has to be. Okay, so we're going to label our equations 1 and 2. Okay, and so there'll be a unique solution for all values of k except where the gradient and the two lines are the same. Okay, so any time that the gradients are the same, then we won't have a unique solution. So basically, we go about solving this in kind of a backwards way, because what we do is we actually find when there is a unique solution, okay, and from there, then what we can do is say, well, all our other values for k will give us unique solutions. Okay, so to find the gradient, we want to write the equations in the general form of y equals mx plus c. So we're going to rearrange these equations. So we'll start with 1. Okay, so we want to put them in the form y equals mx plus c. Okay, so we're going to have to take away our kx. We've got 3y equals 1 minus kx. And I should have written that around the other way actually, but I'll fix it in the next one. Then we'll divide by 3. So we'll get y equals negative k on 3x plus 1 on 3. And that was our equation 1. Okay, we're going to do that now to our equation 2. Okay, so this time we're going to say, well, we've got 3ky equals negative 4x. Okay, so y equals negative 4 on 3kx. Okay, so we're going to have a unique solution. Okay. Okay, so, well, sorry, we're not going to have a unique solution when our gradients are the same. Okay, so if we equate our gradients now and say, well, our gradients are the same, okay, we're not going to have a unique solution because we're either going to have no solutions or infinitely many. So we'll equate our gradients. Okay, now we solve for k. So what we'll do is we'll multiply by 3 and multiply by 3k. So when we multiply this side by, sorry, we won't do that. So we'll go back a step. Okay, what we'll do is we'll multiply by 3k, gives us negative 3k squared on 3. Okay, multiply by 3 gives us negative 12, negative 3k squared, and we get 4k squared. Okay, equals plus or minus 2. Okay, so that means, okay, then we're going to have a unique solution, okay, when k is an element of all real numbers excluding the points 2 and negative 2. Okay, so when k is an element of all real numbers excluding negative 2 and 2, then we will have a unique solution. Okay, so we didn't need to actually work out what it means for k or actually find what our equations would equal or anything like that. We just want to know our values for k. Right, we can go a bit further now. Okay, and look at this with simultaneous equations with 3 variables. Okay, so instead of having straight lines, what we actually have is planes. Okay, so what we can think of is for no solutions, okay, think of it as like 3 pieces of paper in a pile. So we've got one piece of paper, okay, there could be another bit of paper below that, okay, and another bit of paper below that. See, they never intersect. Okay, so these are no solutions, what they look like. Okay. We can also have the case we've got one piece of paper like this. Okay, we have another one, okay, that actually goes through this one, like so. So we do actually intersect. Okay, with these 2 planes, we're going to have 3 planes, and the other plane comes through, say, down here somewhere. Okay, so we actually come through down here somewhere. Okay, so this plane in the middle, this blue one, okay, it intersects with both the other 2, okay, but there's no spot where we have all 3 planes intersecting. Okay, so that's what happens when we have no solution. Okay, when we have one solution, okay, there's only one way this can work, okay, and that's if we have a piece of paper or a plane this way, okay, we have a plane going this way, and we also have a plane coming this way, so that they all line up, and there's just one spot in the middle. Okay, my drawing isn't the best thing you've ever seen. Okay, but basically we have one that's flat, okay, one that's this way, and one that's that way, and where those three intersect, okay, is where we have our unique solution, right in the middle. Okay, and then we can have our infinitely many again. Okay, and there's two ways this can work. Okay, one, they're all the same plane. Okay, so that's where they're all three are exactly the same. Okay, the other way is where it's kind of like the pages in a book. Okay, so if we have one plane there and another plane here, so another plane there. Okay, then down here, this line down here, okay, is where they all intersect, and we've got infinitely many solutions. Okay, so for these we're always going to have three different equations, one that describes each plane. Okay, when solving three simultaneous equations without technology, the strategy is to eliminate one of the variables and reduce three equations with three unknowns to two equations with two unknowns. Okay, solving simultaneous equations with technology becomes a straightforward problem in CAS or using our calculators by using the inbuilt function. Okay, but we need to have a look at what it means to do one by hand. Okay, so what we've got is this following set of equations. 2x take 3y plus 2z equaling minus 5. We've got x minus 5y plus z equaling 1. And we have 2x plus 3y plus z equaling minus 2. Okay, if there's anyone out there that has pretty good skills with matrices, you can solve these in matrices as well, but we're still going to look by hand. Again, you could do an elimination method, okay, which is essentially what you do when you use matrices to solve these, but what we're going to do is we're going to use substitution again. So basically what it means is we're going to get one equation in terms of one of our variables. So we'll call these equations 1, 2 and 3. Okay, so what we're going to do, okay, is we're going to rearrange 2 okay, in terms of x. Okay, so I'm just going to move everything else over the other side. So we get x equals 1 plus 5y minus z. Okay, is what x equals. Okay, then what's going to happen is when I sub x into here and here, it's going to disappear. We're only going to be left with an equation with y and z, and another equation with y and z, and solve them simultaneously as we have. So we're going to sub x into 1 and 3. Okay. So our first equation is going to become 2 times 1 plus 5y minus z take 3y plus 2z equals minus 5. And this one, so we'll call this equation 4 now. And this one here, we're going to go 2 times 1 plus 5y minus z take plus 3y plus z equals minus 2. And we'll call that equation 5. Now, which equation you rearrange for which variable is up to you. I mean, you very easily could have rearranged either of these for z. You could have rearranged one of them for y, but in all those cases, y was a bad call because really you would have been dividing things by 3 and 5 and you were going to get horrible coefficients. Okay, so other than trying to avoid horrible looking coefficients, those are the things we always like to avoid fractions where we can. it's best to go for one of your variables that doesn't have a coefficient. Okay, what we're going to do is expand out the brackets in both of these. Okay, so we'll deal with 4 first. So we'll go 2 times 1 is 2 plus 10y take 2z take 3y plus 2z equals minus 5. Okay, so then we can simplify this. We'll leave our 2 here at the moment. 10y take 3y gives us 7y, and minus 2z plus 2z actually gives us 0, okay, which equals minus 5. So we'll keep working with this one actually because it's looking quite nice because we just solved for y here actually. So what we'll do is we'll take our 2 away, which gives us 7y equals minus 7, so y equals minus 1. Okay, that was a little unexpected. Okay, it's probably actually wrecked this example a little bit because what we should have had to do, okay, is we would have had an equation with y and z in it, and another equation with y and z, and solve them simultaneously like we did in the previous example. Okay, so this example, I don't know if it was just the way I did it or not, has actually turned out a little bit more straightforward than that. Okay, because if you look in, so that was equation 4, because all we've got to do now is sub y into 5, and we'll get our z. So if we go 2 outside of 1, okay, plus 5 times negative 1, okay, take z plus 3 times negative 1 plus z equals minus 2. Okay, we'll expand out these brackets, so we've got 2 minus 5 times minus 1 is minus 5 times 2 gives us negative 10. Okay, minus 2z. Okay, minus 3 plus z equals minus 2. We can go 2 take our 10 is minus 8. Take 3 is minus 11. Okay, minus 2z plus z gives us minus z equals minus 2. Okay, so minus z equals positive 9. So z equals negative 9. Okay, we're not done, but we almost are, because all we need to do now is sub in our z value and our y value into this equation here. Okay, and we'll get our x value. So that means that we've got x equals 1 plus 5 times negative 1, take away our negative 9, so x equals 1, take 5 plus 9, so x is going to equal 5. Okay. Again, I couldn't show it fully because of the example that was in the textbook and the way I did it. Okay. But the reason why I like substitution better, okay, is because at each step you rearrange an equation and end up with an equation like x equals. Okay, if we'd done this, okay, and we had our equations where we had y and z, you would have rearranged one of those, so we would have had, say, y equals something or other. Okay, and then all it is a matter of going back through and subbing in your values, okay, that you find. So we would have found z last, subbed into our y equation, found y, subbed them both in, found x. Okay, so that's why I like to do them by substitution. Okay, and again, you can have ones where you are just finding answers in terms of parameters as well. Okay, so hopefully that's enough to get you through this section.